Great. I think we should start. So good afternoon and welcome everyone. My name is Ludovica and I'm the outreach coordinator of the Future Vaccine Manufacturing Research Hub, or VaxHub. So today it's my great pleasure to introduce you to the second webinar of the platform funding webinar series. Before starting, I would just like to remind everyone that this webinar is public and recorded and will later be available on the VaxHub website and UCL Biochemical Engineering YouTube channel. So I would kindly request all participants to please keep your microphones and cameras off during the presentation, but please do participate using the chat. This said, I think we can move on with a brief introduction to today's event. So as many of you I'm sure already know, the VaxHub has been supporting an ambitious program of innovative research related to the development of vaccines aimed to low and middle income countries. And in this context, we organized a platform funding webinar series to present the great work achieved by several feasibility studies that were funded in 2020 by the Hub. And these funds were actually part of the budget obtained from the Department of Health and Social Care. So today's webinar is about COVID-19 vaccine formulation, and this was a collaborative feasibility study between UCL Biochemical Engineering and the Jenner Institute in Oxford. This project used design of experiments approaches to improve the freeze-dried formulation and freeze-drying process for Chaddox platform vaccines, such as the Oxford AstraZeneca COVID-19 vaccine. So today we will dedicate around 30 to 40 minutes to the presentation of this project, and then allow around a 20-minute Q&A session, for which I would like to invite you all to post any questions you might have on the chat. So it is now my great pleasure to introduce our speaker, Professor Paul Dalby from UCL. Paul is Deputy Head of the UCL Department of Biochemical Engineering and co-directs the EPCRC Future Targeted Healthcare Manufacturing Hub. Paul joined UCL as a principal investigator in 2000, and his research focuses on using protein engineering, molecular dynamics simulations, and biophysics to address key challenges in protein and viral vector formulation, aggregation, and manufacturing. So a warm welcome to you, Paul, and thank you for being here today. I would also like to introduce Dr. Stephanie Frank, who will chair today's Q&A session. She is a lecturer in synthetic biology at UCL Biochemical Engineering too, and her work focuses on engineering protein nanoparticles. So welcome both and everyone who joined us today. And again, thank you for being here. Over to you, Paul.
Great. Thanks, Ludovica. Thanks everyone for coming to see this. I'll just share my screen.
Yes, please.
Make sure it's the right one. I think it's this one. Yeah, and then. Okay, can you see that?
Yeah. Great.
Okay, so thanks everyone. Sort of very happy to come and present this work, which we did as part of the VaxHub in a feasibility study. So as you can see, it was a collaboration that Sandy Douglas and I had already sort of begun quite early on, and then Cheng Tsang, who's done much of the work on the UCL side, and Adam Berg on the Oxford side. Okay, and it's really about coming up with a freeze-dried formulation for the Chaddox platform, which actually is a platform aimed at many different diseases, not just COVID. So I guess the real idea is to get to the point where we can have vaccines that don't need a cold chain. So typically we're, as you've seen with the Chaddox vaccines, it needs to be refrigerated, and other vaccines need to be frozen. So, in certain low and middle income countries, that's not always possible, not all the time. So having something more stable is really what we were looking for. So the approach we were taking was to go down the freeze-dried route, simply because they're normally more stable than liquid formulations, and we'd sort of aim to do some design of experiments to get that formulation going, to understand what formulation might work best in a freeze dryer using the pilot scale freeze drying facility at UCL. And the idea was then to optimize it for stability, potentially something like 3 to 4 months for up to 45 degrees C was considered as a target, but also to look.
Gary is currently unavailable.
Okay.
Please leave a message after the tone.
I guess that's Gary joining.
Sure.
We're looking for improving cake appearance as well, because that's considered a feature of a freeze-dried material, that it should look presentable as well, not too variable. We aim to evaluate the performance of the freeze drying in terms of the particle size distribution once resuspended, and also to minimize aggregate formation and validate that in vial scale. So we start off in microplates. And actually we went a long way beyond those objectives, because once it looked successful, then we started to look at measuring potency loss. That was done in Oxford, assessing in vials for the variability, characterizing the materials, the freeze-dried materials in terms of the melting and glass transition, and generally put in a lot of work to improve the freeze-drying process as well, which I'll discuss as we go through. Okay, so just to kind of bring you to the background, clearly this is a sort of a cartoon version of how we get to the point of administration of a drug or a vaccine, and this would be a typical liquid formulation route. And at some point at this stage here, where you do the filling stage, we would take it out. We're looking at freeze drying, so you could implement a solid version there. Okay. So one thing I'll do is just sort of give you an idea of where the current state of the art is. And so these are kind of previously published adenovirus formulations. There's a liquid formulation in this paper here, Evans 2004. And you can see their survival this is how much loss you get. Certainly at 37 degrees, just over a month, and you've lost 80% of it. In the fridge, even over 180 days, you've lost 25%. So it's usable, certainly when you go to 4 degrees C storage, but less usable as you go to 30 degrees C and upwards. And then the kind of state of the art in freeze-dried formulations, what we call the Chen formulation, that essentially had a freeze-drying process where half of the material was lost just getting through the freeze dryer, and then a further 17% stored for 180 days at 4 degrees. So quite considerable loss overall, and then at 37 degrees, again, a total of 85% loss. So there's a lot of room for maneuver, but at least then we had a kind of a starting point in terms of formulation to base our work on. So that was the idea. For those who are less familiar with freeze drying, this is kind of what it looks like. We have one of these, a Lyostar, sat in our pilot plant, and essentially you go through various stages. You freeze your material, you then apply a vacuum so that you can start drying or subliming the material for some period of time, and then you might increase the temperature to go into a secondary drying stage. And there are variants of this, and I'll discuss some as we go through. After that, you stopper, and then we inspect the cake, store it for a period of time, maybe at different temperatures, and then reconstitute and measure dynamic light scattering for particle size distribution and the infectivity, which is done in Oxford. So all of this kind of based on some much earlier work we'd done in collaboration with the National Institute of Biological Standards and Control, Paul Matashuk, where we had implemented the use of microtiter plates in freeze drying, really with a view to doing design of experiments, rather than kind of lots of vials which use lots of material. And so what we had done in that work was to map thermally using infrared imaging cameras the temperature distribution across the plate, which actually was a small factor. It was fairly uniform across the plate, and also looked at the rate of sublimation of water out of wells, and we could see that there were kind of the outer wells were subliming much faster than the inner wells, And so our designs from then on were to have an outer sort of ring of water, and then all of our formulation samples on the inside where it was reasonably uniform. And again, that previous work, we had already shown that we could use design of experiments. We typically used central composite face designs to get an optimal formulation, and we had validated that in vials and shown that the predicted from microtiter plates and the vial performance were in very good agreement, which shows the design of experiments approach works really well using microplates in freeze dryers. So that was the basis, and the sort of plan of action now to do the formulation work for the ChAdOx platform. So I'll move into what we got. What I don't want to do is to go through every single stage of the design of experiment formulation design. There's quite a few kind of stages we did, and some blind alleys as well, but this is sort of an overview of the sorts of approach. So I'm going to go number things by stage in terms of we did these things in this order, but stage 3 was a dead end, so we're not going to look at that one much. We started off with a simple 2-level factorial screen of a number of different excipients, much of which you will have seen in that Chen formulation I showed you earlier, and spanning the kind of concentration range used there. Having kind of done that work, we then went into more detail with a 3-level approach, and then we looked at this sort of higher sugar one that didn't work. We had a fairly standard freeze drying protocol, and the platform we were using was ChAdOx one that has luciferase gene, so it's that facilitates the infectivity assay, and we're looking at 6 × 10⁻11 virus particles per mil as our loading. So the first stage, having run it in microplates, you could see pretty good cakes appearing, the solid phase up in the top right there, and we can plot out the main factors shown in this Pareto chart here. So we could see that D, which is mannitol, was having a strong impact on the performance in terms of titer loss, and also sucrose and trehalose, which are no great surprise. But we could also see that there were interactions that were significant. Anything above this red line is significant. So A and D tells us that trehalose and mannitol are interacting, for example, and F and H are arginine and the buffer, which is a little surprising. And then if we look at individual factors, you could see which way they go in terms of the impact on titer. So we can see that going from -1, where you don't have any mannitol, up to 1, where you have the highest concentration, you get an improvement in the titer, and same with sucrose and trehalose. And the other factors are much less kind of obvious in terms of not doing much. And in fact, we decided magnesium chloride might not be important to put in at all. And a rule of formulation is if it's not doing anything, take it out. Okay, so we also did a quick comparison of performance from the plates with performance in vials. And we could see that we were getting roughly the same kinds of titer loss between vials and plates. So we're quite happy then to move on using the microtiter plates. So stage 2 was to explore in more detail, because previous stage was only 2 levels. It doesn't really tell you where the optimum is. So we put in a 3rd level. So we have now a low, middle, and high level. And we also increased the concentration range for trehalose and sucrose. That's because, as you can see here, they seem to be going up, and we're not yet reaching a maximum, so we could add more. So we went up to now 15% of each of those sugars. Same with mannitol. Shifted the pH to a slightly higher range, and then we also eliminated one of the buffers and just fixed histidine and looked at the concentration of that, and also tween. We kept arginine and we got rid of magnesium. So some changes, but mainly to explore higher concentrations. So we performed exactly the same freeze drying in microtiter plates, and you can still see trehalose is important in terms of titer change. Sucrose is important. Mannitol has a self-interaction DD, which is because it has an optimum in the range. So we can see that there is actually a point where mannitol becomes negative impact on titer. So mainly trehalose and sucrose and mannitol, a little effect from arginine. Now, interestingly, we decided to measure the cake, and we score the cake manually. We look at them and have a sort of a range of images, and we score against those images on a range of 0 to 10, and we can determine how good the cake is and do a DOE analysis based on that score. And we saw similar important factors, trehalose, sucrose, mannitol, but in opposite directions to the titer. So there appears to be a trade-off between getting good titer and getting good cake, which is a bit of a pain because you want both ideally. And it was an almost exact mirror in terms of trade-off. So this creates a bit of a conundrum. Certainly titer is the most important feature, so that's our primary objective, because you don't want to lose potency. So I've gone past stage 3, which is where we explored higher sugars and ran into more trouble, but the next thing to do was to characterize some of these formulations, to get a little bit of understanding as to what causes titer loss when it happens. So we took some of those formulations shown here by their order number, and we went out and measured using DLS the average particle size, the polydispersity index, which is a kind of an indication of how many different peaks you've got in terms of different sizes. And also we measured the viscosity of the solution as well to see if that was having a major impact. We measured their melting temperatures and also their aggregation temperatures in once reconstituted. This is all reconstituted after initial freeze drying. And quite interesting, we see that most of the titer loss, the biggest losses, occur when we get bigger particles forming. So it's due to aggregation of the viral vector into larger particles. And you can also see that through a higher polydispersity index. So certainly the worst cases are due to this aggregation. The differences up here are more harder to discern in terms of really not much to do with particle size. If we look at that in a bit more detail, you can kind of characterize the particles sizes a bit more, because what I showed you before was the average particle size, but actually you can categorize them into different peaks that you can see and their populations. And we can see the good formulations out here on the right are the ones where it's primarily in this range, 80 to 200 nanometers, which is about the size of the particle as you start should be around 150. The middle point ones have got mainly only observable that size, and then the bad ones you start to get lots of very large particles and potentially some fragments as well showing up down here. So fragmentation might be also an issue in poor formulations. So the trade-off was a bit of a conundrum, as I said. So one thing we thought about was, what can we do to improve the cake in other ways that might not lose the titer? And a classic way to do that is to put into the process what's called an annealing step. So we're using mannitol, for example, in our formulations, and that's known to be not properly crystallized if you quickly freeze it. So you get into a glassy state. And so one thing you can do is just take the temperature back up briefly. It's still cold, it's like -28, -30, something like that, but originally freezing at -40 or -50. You take it up a little bit, and that allows some more crystals to form. So it kind of gets you a more crystalline state, which hopefully would improve your cake morphology, make it look nicer and not all kind of melting. So we tried that. We tried looking at a different set of annealing temperatures from -28 up to -7, and we could see pretty much compared to no annealing, everything improved. -7 perhaps still a bit patchy, but somewhere between -10 and -28, we were getting reasonable consistency across the formulations compared to having no annealing. So annealing was having a good impact on the cake structure. So we took that forward. Another stage we did was just to say, well, if it's working, should we extend it, like do longer annealing steps and also dry the samples even more? So at the secondary drying, to leave it for a lot longer so that you get rid of as much moisture as possible. So a really long duration for that. And that did improve the cake morphology. And you can kind of see what's going on overall with titer and cake score with these two plots left and right for the different stages. So stage 2 is without annealing, stage 4 is with annealing, and stage 5 is with extended annealing and drying. And if we were focusing on the cake score, that was getting progressively better, so the logic was paying off, and all of our formulations were improving in cake score. But you can still see we had this issue with trade-off, where many of the formulations were nosediving into really poor titer losses, although our what we called the optimal formulation, which was the predicted optimum from our DOE, was actually still quite robust, so we could get a good cake improvement and retain the same titer. So hopefully we're able to sort of beat the trade-off with some of our formulations in these conditions and this process. Just to kind of note, there was other literature out there, I think from GSK, that sort of looked at these kind of issues, and they found that if you dry it too much, you can also lose titer. So viral vectors don't like to be very dry, but the problem is if you don't dry it enough, your cake will collapse back and melt when you warm it up again to room temperature. So it's a real kind of art to getting the right amount of drying. Okay, so that's all done in microplates so far. One thing we needed to establish was whether now shifting into vials, we're going to change everything. We had done that work at the beginning to show that the vial performance and the plate performance was similar, but you just never know. So what we did was we took our best process up to this point and the top formulations, or actually a range of formulations, into vials, and we used a 650 microliter fill in 2 ml vials, so standard freeze-drying vials. And what you can see here is kind of a distillation of everything with the current process. This is the titer performance for any given formulation against its cake performance, and you can clearly see these are the microplate results in blue, red, and black from those first stages 2, 4, and 5, where we started annealing and extending it, overlaid with the vial performance in green. So you can see that trade-off. It's like a Pareto front trade-off between the two. But you can see now the vials are kind of hanging out in this top corner here, which showed us that whilst not exactly performing the same way as the microtiter plate data, they were generally better in performance in terms of the Pareto front, at least, maybe not on an individual axis. So that turned out to be really quite encouraging, that we could switch to vials quite happily. I just want to show on here particularly the optimal formulation, which is circled in red. They're the stars. So you can see these, the titer is robust. Okay, so the optimal formulation, regardless of the process, gives different cake scores but keeps the same titer. And so actually the vial sat somewhere here at a score of about 0.7, which is okay actually for good enough, I would say, in terms of cake performance. There are other formulations such as these filled circles, which I think is DOE 14, and you can see it's extremely sensitive to the process. So it goes from having a poor cake and high titer all the way down to poor titer and great cake. So it's some formulations respond a lot to the conditions and some are more robust to the conditions. Okay. One thing we were interested in doing was working out what's actually happening. Why is the cake not looking good? So Chen came up with the idea of putting a camera in front of the freeze dryer and actually filming the process and tracking the images against what we're actually doing. So in the freeze dryer, we can measure, this is the pressure applied, the vacuum applied essentially, the temperature it's at, but also you can track the amount of water coming out. So it's got a sensor on it that determines how much water is being removed. And you can see a lot of water being removed in this primary drying phase, and then it kind of comes to an end. And then when you suddenly increase the temperature, reduce the pressure, you get these bumps in water coming off. And it's at these moments that little bubbles and cracks started to form in the cake. So it was kind of the sharp changes into different drying phases that were causing bumping at particular points and deformation of the cake. So we figured maybe the thing to do now is to make it a little bit less extreme. So we did it again, and this time put in slower gradients, so it wasn't quite as abrupt. And you can see that means you get less of a spike in the water drawn off, more of a kind of a slow hill. And that indeed did improve the cake appearance. We still got some bumps and holes, but it was a lot better. So we could just smooth it out and improve the cake performance, cake appearance, without changing the formulation. So hopefully without changing the titer. This is just a side-by-side of the images, and you can see this is the sort of stepped gradients on the left and the smooth gradients on the right. And you can see equivalent vials are a little bit better in appearance on the right than they are on the left. So that's very encouraging. Should just point out though that all of our work was at a fairly shallow fill in microtiter plates, and the cakes in there were perfect, right, or nearly perfect. Whereas it's going into the vials where we start to see the differences. And it seems to be that there's a kind of a really near perfect layer in the top half of the vial, and the bumping tends to concentrate at the bottom of the vial. So we then thought, well, maybe we can adjust the fill volume and try to see how important that is on the performance, because that's the main difference. So we looked at fill volume. We went from 200 to 1 mil, 200 microliters up to a mil fill. And these are the cakes that come out. We can actually see 650 is the worst, and 1 mil seemed okay. So kind of something to do to understand why that happened. In terms of appearance, and we took those samples out and went back to measuring the glass transition, and you can see this is the calorimetry work that shows where the glass transition is. So this is the kind of the transition point between an amorphous state and melting. And you can see that the small fill volumes are in green. They've got a much higher glass transition in the solid phase here of around 40 degrees, largely due to sucrose, than the higher fill volumes where the glass transition comes down really low. And you can see then this might be why we get problems, because this can melt quite easily, cause meltbacks. It's less stable. Okay, so that could be one reason behind it, the lower TG. And then hot off the press, actually on Monday, I think this data came, so it doesn't yet have error bars on it, but this is the titers after 50 days incubation at 4 degrees and at 30 degrees, compared to what initially goes in. So this is the titer you start with in black across the top. These are the different fill volume samples being reconstituted and measured for infectivity. And you can see after incubating them at 4 degrees for 50 days, you do see losses compared to what you start with, but it isn't nearly so bad as obviously the 30 degrees where you sort of heat challenging it more. But the main kind of result out of this is you can see the higher fill volume has really quite severe drops at 30 degrees when you go to the higher sort of volume, which tells us that these aren't very stable at all compared to the lower fill volume ones. Again, we need to see the error bars before we can judge exactly where they stand, but it seems then that the samples with lower TG, to these ones up here, in the higher fill volume melt more at 30 degrees C, and that's losing infectivity. So that seems to be telling us that a viable way forward is to reduce the fill volume to 200 microliters. Okay. I should add, this was done with one of the older processes, and that's now also improved since, so that the cake appearance is generally better, the slow annealing, because this was done with an earlier one, with the step annealing, I think, the step temperature change. Okay, so that is where we are, and I think I can just pull all that together in terms of how it's performed. So these are, excluding that data I've just shown you at 50 days, this is kind of the performance of those different formulations, the optimal formulation, sorry, from DOE after a month at different temperatures, and we can see we get 90 degrees C, 90% remaining titer at 4 degrees, and 25% at 45 degrees, which is actually pretty good. And when you compare the Chen formulation, 37 degrees for a month, which I guess closely somewhere between this one and this one, it was only 15% remaining, and most of which was lost in the freeze dryer itself. So we've gained quite a good advantage on the existing formulation in terms of being able to store at something like 30 degrees and still get decent titer back. And these numbers will improve because of the new process as well. We had this trade-off between cake appearance and titer, but slowing the process down and the gradients down appear to have improved that. The lower fill volume also appears to improve it. I've put this question mark here. I wrote this before I got that data on the previous slide. So watch this space. You're now watching this space. It does appear to be that the titer is improved, or doesn't get lost. So it's not really on this trade-off in the same way as it was before. Fingers crossed. So it looks like we've got an improved formulation with good titer and a decent cake appearance. So that's everything, and well, thank you for listening, certainly, and I just better make sure I acknowledge again Cheng and Adam, who did the work, and Sandy and for kind of helping this collaboration along, VaxHub for support, couldn't have done it without you, and also this grant here, which is what got us the freeze drying kit in the first place, and supported Cheng before we came into this. So thank you very much for listening, and I'll be happy to take any questions.
Thank you so much, Paul.
Got a real clap, of course. I got a live audience.
Oh, fantastic. Your own fan club, Paul. Great. So please post your questions in the chat. I'm going to read out the first question to you, Paul. It's
Sure.
from Warren. Do you think that the bumps arising from rapid pressure changes would be more of an issue at small scale rather than at an industrial scale freeze dryer?
Well, I think it might be quite similar because the freeze dryer is a pilot scale freeze dryer. So the vial dimensions are all as you would use them. So they're no different. I guess there could be on a really large scale, I would imagine, if anything, less of an issue because changing the temperature and the pressure in the larger scale freeze dryer would be less abrupt. But how much impact that will have, I couldn't exactly tell you. But I suspect it won't be a massive impact. I think once we've got to this scale in the pilot dryer, it's reasonably comfortable. There may be some fine-tuning to do, of course.
Okay. Cheng added to this, it is actually the shelf temperature rise. So I guess this was related, yeah, to your answer.
Thanks, Cheng.
Correcting. Yes, I had a question myself, actually. You talked about the higher fill volume having a severe effect and the need to reduce the fill volume. I may have missed this, but do you have an explanation for this, Paul?
Yes. So if you look at the vials themselves, you see you have this kind of solid crusting at the top, kind of what is actually a nice cake at the top, and it's a little bit kind of bubbly at the bottom. If you imagine what's happening in the freeze dryer when you have a high fill volume, is that you're getting sublimation from the top, and it can start to it forms a crust early on at the top, right? Because that gets drier, and then what happens is you've got this more moist material behind it, which is now the moisture trying to force its way out, right? So you effectively get to the end of your drying where you've got very dry material on the top and less dry material on the bottom, and the less dry material has a bigger tendency to melt back, right? So when you go up into the primary drying and then up into secondary drying, this can remelt essentially because it isn't dry enough, and that's where you get your bumps. So it's quite a challenge because you want to form this cake nicely, but it needs to be porous enough that the moisture can get through it easily.
I see. So it's a bit a more heterogeneous sample just due to the volume. Yeah. And what do you have certain parameters that you said you visually look at your cake morphology? Are they kind of, do you have a set of parameters you tick off or you score?
Yeah, we have the Cheng scoring parameter chart. He devised it a while back where we took kind of 10 typical typical looking vials and ranked them in order and then scored them 0 to 10. And then, yeah, so they've got different amounts of kind of cracking and bubbling in them. And so Cheng and then Adam separately look at the images and score them, and then they combine their scores together. So it's kind of a semi-subjective, semi-objective, let's say, approach, but it seems to work.
Yeah, it seems to work. Great. Thank you, Paul. We have a few more questions now coming. Adil is asking, how transferable would you predict this for other particles to be?
As in other viral vectors?
I assume so, yes.
Yeah. Tricky to say. So, you know, if you look at what the GSK work, I think they did it on AAV. So there are similar issues that come up in terms of over drying causing problems. So I think broadly the same kind of overall effects might happen, and then you have to optimize them in similar ways. But in the end, the actual formulations are different. I think there's enough difference between them that you'll end up with different formulation or different things added in just to get it right. So that, as ever with formulation, there are usually some sort of general underlying trends, and then exceptions to the rule when you change your particle. That's what I would expect. So I doubt we could just lift in a different like a different serotype or a different vector entirely and expect it to behave the same.
So I guess the excipients would be quite different, and also the kind of aggregation behavior and so on, depending on the virus properties. Yeah. Okay, thank you, Paul. So there's another question here from Steve. When changing fill volume, are you also compensating for viral concentration? So the vial contains the same number of doses.
Yeah, so you can see here on the right, they all contain 10 to the 11 viral particles per mil. So it was different concentration, but we also did a 200 microliter with a higher concentration, so it ends up being the same overall dose. So we did both options and compared them. And actually, I haven't shown this in this image, but the 200 microliter one had, I think, 3 times as much in the other version of it in terms of virus particles, which ends up being equivalent to this total dose in the 650, I think. And yeah, it behaved pretty similarly. There's some, preliminary data that needs to be perhaps repeated just to double check. But yeah, it looks like the actual viral loading doesn't have that much impact on the freeze drying.
Okay, great. I had a very basic question. I don't know much about freeze drying, Paul, but what is the annealing step? So what's annealing mean?
So annealing is just where, so you freeze quickly, right? So you take it down to minus 40 or minus 50, so it freezes. And it's a bit like when you're making ice cream, right? If you freeze too quickly, you just get a glassy kind of frozen state. It doesn't have time to properly crystallize. Okay, so the water just sort of locks into glassy state with the excipients, the sugars mainly. And if you then just increase the temperature a little bit, it takes it back towards the melting temperature, but not quite. Then it allows the equilibrium to shift in terms of the morphology, and it allows crystals to begin to form again. They nucleate, and that's the annealing step. So you can anneal the formation of crystals, and you're after that because it creates a crystalline material is more likely to form and a cake appearance at the end.
Okay, thank you for explaining that, Paul. I can't see any more questions. Does anyone else have any questions? Post quickly. Is there any questions in your room, Paul?
I don't know. Yeah, there is. Sebastian. Why does the cake appearance matter? I've just been asked. This one's a debatable one, actually. So the regulatory agencies have some requirement for things to look consistent and robust, but I think there's also a marketing thing here. If you kind of turn up with vials and give them to a consultant or a GP, and things look kind of a bit like this one here, there might be a bit of nervousness about sticking it into someone's arm, I think. So the debate is whether how essential it is, because obviously if the titer is being lost in the neat ones, but not in the kind of messy looking ones, then you could probably make justification to regulators that we're not so worried about this. But so it's yeah, you have to do more convincing, let's say, to the regulatory agencies if you've got something that doesn't look nice.
Yeah, that makes sense. So we had, sorry, there's another question in the chat here now. Is the cake, so are the cake parameters, I guess, important for reconstitution or the cake appearance?
Yeah, they are actually. So one thing we have done is looked at, obviously everything gets reconstituted to do infectivity assays and our biophysical assays. At one point we were kind of resuspending in buffers, and then we switched to resuspending in water, and everything looks fine. Everything redissolves really quickly. So I think the answer to that is yes. It's important that they resuspend easily. But nothing so far in what we've seen has shown them to be resuspending too slowly or forming particles or anything like that that are just not dissolving as opposed to particles due to aggregation. So we would flag it up obviously if it happened, and then yeah, you might have to change formulation if it happened. But these sugars tend to dissolve pretty quickly.
Thank you, Paul. Maybe perhaps one final question from me. It would be in industry, how is cake morphology analyzed? Is there some kind of automated way, or is it not really looked at? It's, at development stage it is looked at, and then
I mean, you can measure a lot of things. So you can take a liotherm analysis, which looks for how glassy or amorphous things are. You can do powder diffraction, X-ray diffraction, so you can look for crystallinity. We use DSC as well to characterize it. So they're kind of all quite indirect measures. You can try and image it. I suppose you could start to look at trying to get down to better imaging of the crystallinity of it. You've got the freeze drying microscope, which we do as well. So that shows you kind of changes as well, but it's hard to, we kind of didn't get that to work very well because of the high sugar content in these. So there are kind of measures you can do, and they are often done in the final characterization. As people do studies on different morphologies of, say, mannitol, right? You get it in different, I guess I'm not sure if it's the right word, isoforms, but different kind of states, and you can measure that, particularly I think X-ray diffraction, powder diffraction though.
Mm-hmm. All right, thank you. Can't see any more questions at the moment here, so I think thank you very. Oh, hang on, there's another one, Paul. Even though thermal mapping showed even temperatures across the plate, why did sublimation vary?
Yeah, so that's due to a vapor pressure issue. So if you imagine you've got your plate, so what you remember what you're doing is you're removing water, and it forms like a vapor layer in the chamber, which is being removed. You have a kind of an escape route out of the freeze dryer. But if the vapor pressure is kind of building up over the plate, then it's more likely to build up over the middle than it is around the edges where there's no water vapor being produced. So you get this edge effect. So that's one reason. The other is that you'll notice, if I could play this video again, it isn't perfect. You do get some kind of edging on the temperature. You can see it's like a hot potato effect where it cools into the middle. So you do get different thermal conductivity in the middle compared to the outside, right? Because you've got contact between these wells, which are kind of a similar temperature, but not being equilibrated to the outside temperature quite as easily, other than through the top and through the shelf. So there is a bit of a thermal distribution across it, which may well be due to this, give some of this difference in sublimation. One hopes that you're removing the vapor quickly enough that the vapor pressure above it isn't an issue, but I think it is.
Thanks, Paul. It's It's very clear. Okay, I think now there's no more questions, so I think I will thank you again very much, Paul, and thank you for the questions, everybody, and I'll pass back to Ludovica now.
Great, thank you.
Thank you. Thank you, Steffi, and thank you very much for very interesting and relevant presentation. I'm going to share my screen again because I would like to conclude introducing you to the next webinar of this series. This is going to happen next week on the 16th of February. Same time as today, and the feasibility study title is Validation of the Minitem system as an analytical quality control tool for vaccine and viral vector manufacturing. This is a study that was conducted as a collaboration between Vironova and UCL. So I hope to see you all there. I'm going to share the link to register here in the chat. You can find it as well on our social media platform. And that's it. Thank you, Paul. Thank you, Steffi, for chairing the Q&A session. And thank you, everyone, for joining us. Hope to see you next Wednesday. Thank you all. Have a great day.
Thank you.